Hi guys, welcome to another one of my lectures, RT Daulat, and today we'll be looking at a foundational topic for both csec and CAPE, right? And CAPE Unit 1 in particular, we'll be looking at wave theory. Now, one of the things that we will deal with in this lecture is talking about what a wave is, ways to represent it, as well as properties of the wave. In subsequent videos, I would look individually at sound waves, light waves, and electromagnetic waves. Now, when we talk about a wave, I always introduce a wave in terms of energy. And when you talk about what a wave means in terms of energy, it means it transports energy. So there are many different forms of energy, and if you think about how a wave is generated, everybody knows about waves in a beach, right? And if you think about it, there must be some kind of source to provide this energy, and then you have the molecules in that medium. In the case of water wave, it's water molecules, and these molecules becoming displaced from that equilibrium position. Now, when these molecules become displaced from that equilibrium position, you will find that they will transport the energy through that displacement. And you must have a source introducing the energy to the medium. Now, when we look at subsequent videos with electromagnetic waves, you will see that you may not need a medium to transmit energy, right? And that is where you use force fields, for example. So here, when we talk about wave and we relate it to energy, it talks about the transportation of that energy. So I will now consider my molecules in equilibrium position, right? So when my molecules are in equilibrium position, we will have a disturbance. And the disturbance is like me, let's say, throwing a stone in water, right? And it generates water waves. Now, what this source will do is that it introduces energy to the water molecules. And what happens is that these molecules will become displaced from their equilibrium position. When that happens, you have this kind of hill and valley pattern being formed. Now, this actually is a sinusoidal representation of a wave. A sine wave, it's a mathematical function, right? So we can show the displacement of the particles being analogous to that hill and valley, if you may, or sinusoidal wave function. So if we want to look more closely at this representation, let's let the x-axis represent rest. And we can show, right, instead of using hills and valleys, I could call this one the crest, and I can call this one the trough. The other properties that are seen will be amplitude, which is the height of the crest or the depth of the trough, and amplitude is a distance measurement, and it is defined as, so it's measured in meters, and it is defined as the maximum displacement of particles from rest position. Okay? Now, another thing I can show is one cycle of the wave. So one cycle is actually a crest and a trough, and that is denoted by an upside down Y, which is a symbol for wavelength, the lambda. So like the name suggests, a wavelength is the distance traveled in one cycle of the wave. Right? Distance traveled in one cycle of the wave. Now here, another way that we can represent a wavelength is by showing you 2 points that are in phase. Alright, so I'm going to put a point A at the top of the first crest, And at crest number 2, which is the second subsequent cycle, I'm going to put another point B. So based on this diagram, you can now see the directions in which the particles are traveling. So now we are looking at A and B being in phase, and the separation of 2 points which are in phase are considered to be one wavelength. So A and B have 4 characteristics in common. They're on the same side of rest position, they are traveling in the same direction, they are having the same velocity, and they are having the same displacement. So because of that, they are found at the same point on adjacent cycles, and therefore the distance between the points are in phase. Now if I looked at another point, let me just say perhaps this point here, C, they clearly are on opposite side of rest position from A and B. It's traveling in a different direction, and therefore it is said to be out of phase. Points which are out of phase are described to be half of a cycle or half of a wavelength apart. Now the other property I want to talk a little bit about is the period of a waveform. So here we're going to look at one cycle being a crest and a trough, right? And capital T represents the period. Now the period T is a time value, and it is the time taken for one cycle to be undertaken, or the time taken for one cycle to travel. Okay, now it is a time measurement, and it is measured in seconds. Okay, so now let's look at a second way that we can represent a wave, and that is as a wave front. Now a wave front is simply a line drawn joining all points in phase with each other. So if I had a basic waveform like this, and I simply took a line joining, all points like this, I'll get a series of parallel lines. So you can have either plane wavefronts, or you can have circular wavefronts. So your plane wavefront is a series of parallel lines. The solid lines represent crests, and the space in between represent troughs. So in the same way, you have semicircular lines. The solid lines represent crests, and the spaces in between represent troughs. Now the distance between adjacent lines will be a wavelength, and in the same way, in the circular wavefront, the distance between adjacent lines will be a wavelength. Now, we started off the lecture by discussing how the particles in a medium become displaced. And now let's examine particle movement in relation to wave movement. Now, if my particles are moving up and down, so they have a vertical disposition, and my wave is moving left to right, then I can now say that the particle movement is perpendicular to the wave movement, and that is characteristic of a transverse wave, where the particles move perpendicular to the wave. An example being things like light, water waves, electromagnetic waves. Now, if I look at a longitudinal wave, I have my wave going left to right, and my particles are now vibrating parallel to that wave motion. So therefore, that is described as where the particle motion is parallel to the wave motion. And a common example of longitudinal waves are sound waves. So if I were to represent, let's go back to the sinusoidal representation of a wave. and I have a displacement time graph. And I show here the sinusoidal representation. It doesn't matter if it is a transverse or longitudinal wave. I cannot deduce that from this representation. What I can deduce is the two main things that can be deduced from a displacement time graph are the displacement A, which is the height of the crest or the depth of the trough, and that could be read off from your y-axis, and the time taken for one cycle, which can be deduced from your time axis. So if the period is the time taken for one cycle, then I want to introduce you to a concept called frequency. Now, frequency is the number of completed cycles in 1 second. And it is basically the inverse of the period. So frequency is measured in a unit called the hertz, and the frequency is 1 over the periodic time. So the hertz is actually per second. Okay. Now, consequently, if I had, let's say, a displacement distance graph, right? Now let's look at the displacement distance graph, right? And again, I could represent a sine wave to be either a longitudinal or transverse, and the two deductions I could make is the amplitude, which is the height of the crest or the depth of the trough, and also the length of one cycle, which is one wavelength, right? So now we can kind of put together everything that we have learned. So I want you to look at this formula. Speed is distance over time. So let's represent speed by v, and for one cycle, the distance traveled is a wavelength and the time is 1 period. So lambda over t can now encompass a formula for speed. But 1 over t is equal to the frequency. So v is equal to f lambda. So I just want to point out, guys, that these are the two main formulae. We're going to say v is f lambda, and we're going to say f is 1 on t, that you're going to use when it comes to wave theory. So how do we categorize something as a wave? What does it mean to be a wave? For a substance to be considered as traveling as a wave, transporting energy as a wave, it must exhibit 4 properties: reflection, refraction, diffraction, and interference. And what you are going to notice is that we're going to examine these in more detail. So when you have a wave having a property of reflection, it means that it encounters a medium where it has rebounded. So the only property of the wave that changes in the direction is the direction of the wave. So I can represent that very simply by showing a series of plane wavefronts, and I show the direction of travel of the wave as always perpendicular to my wavefronts. So here, if I let this line be the reflecting medium, what happens is that as it encounters the reflecting medium, the only thing that changes is the direction. So the shape of the wavefront, the wavelength, everything remains the same. Now, when I talk about refraction, a lot of people had met that prior to waves in terms of looking at light, right? So refraction is where my wave bends, changes speed and wavelength when it goes from one medium to another. And this is because the density of the medium changes. So its speed, its wavelength, even the angle at which the wave is directed to the medium changes. And this is what we term Snell's law. Snell's law states for a wave traveling from medium 1 to medium 2, the ratio of the sine of angle of incidence to the sine of angle of refraction remains constant for all angles of theta. It just says that if your wave is going from a fixed medium 1 to a fixed medium 2, regardless of its orientation, the angle of incidence and the corresponding angle of refraction, the sine of those angles will represent a constant value. That constant value is the refractive index, which tells you the extent of refraction that has occurred as your wave goes from one medium to the other. And in refraction, you have the angle, you have the wavelength, and you have the speed changing. And the only thing that remains constant is the frequency. And many times we look in water waves as a wave going from a deep to a shallow region. And in the deep to shallow, it's two different media. So the speed in the deep, the wavelength in the deep, and the angle in the deep is greater than the speed in the shallow, the wavelength in the shallow, and the angle in the shallow. So many times you could just show here as like if you have your normal here. So you have your angle of incidence, and this is taken from light theory, and then you have your wavefronts being perpendicular here, right? And we represent theta I as the angle between the wavefronts and the surface. So this is deep and this is shallow, and we have our wavelength here, lambda d, right? So many times you would have noticed that your wave refracts here, and if it slows down, your angle is smaller, right? So then now, perpendicular to this, we can show how the wave behaves, right? So we could even go on to show more, use yellow here. Could even go on here to show more wavefronts, and then you show how they behave here. So the lambda in the shallow is less, the angle is less, and the velocity is less. And we could even, put this together as Snell's law, where this represents the refractive index going from 1 for the wave traveling from medium 1 to medium 2. That's a ratio of the two refractive indices, which is a ratio of the speeds, which is a ratio of the wavelengths, which is a ratio of the angles. Right? So let's look now. V1 will be the speed in medium 1. V2 is the speed in medium 2. Lambda 1 is the wavelength in medium 1. Lambda 2 is the wavelength in medium 2. Theta 1 is the angle of incidence in medium 1. And theta 2 is the angle of refraction in medium 2. Right, so now let's look at diffraction. Diffraction is basically the spreading out of the wave, right? So when the wave encounters a gap or obstacle of comparable size to its wavelength, it basically begins to spread out. So let us consider here now a series of parallel wavefronts, and they are going to encounter a gap. Now you're going to compare the size of the gap d here to the wavelength here, and obviously d is greater than lambda. So when that happens, you don't have a lot of spreading out as the body of the wave passes straight through. Now the wavelength here is the same, and you would tend to have minimal diffraction. Consequently, if you have maximum diffraction, that would occur whenever d is approximately the same as lambda. So here I would have my parallel, I would have my parallel wavefronts, and then I am looking now at the size of the gap being about the same as the size of my wavelength here, and that is the formula to have maximum diffraction. So maximum diffraction is basically where I have a circular wavefront pattern now being generated. And again, this separation, the distance between subsequent wavefronts, is one wavelength. So what I will notice is that in diffraction, the only property that changes is only the shape of the wavefront. Only that changes. Okay? Now, the last thing I want to look at is moving from diffraction, which is interference. And basically, diffracted waves will tend to interfere with each other either constructively or destructively. And that is also termed superposition. So what you will find is that if I take a crest and a crest and a trough and a trough and they overlap each other, then you would have a larger waveform being generated. And if I have destructive interference, that's basically where a crest and a trough overlap, and I have destructive interference. So interference is where two waves of, well, they can have the same frequency overlapping with each other, right? So let's consider two waves here of the same frequency. So you have wave A, and then you have wave B. Now these two have the same frequency, so at any point in time, I have them totally overlapping. I have crest and crest, and I have trough and trough totally overlapping. So what is the result is a larger waveform being generated. Now, in the same way, I could have destructive interference. So that I spoke about just now is constructive, right? So in destructive, I have wave A, but when it overlaps with wave B. So now I have a situation where the crest and the trough of subsequent waves are overlapping. So when that happens, it results in the cancellation of the wave. And that is indicative of destructive interference. So let's say I have a source S1, and S1 is generating circular wavefronts, and I have another source S2, and that is doing circular wavefronts as well. I could show on this diagram constructive and destructive. So here I have crest and crest overlapping, and where the two spaces overlap is trough and trough. So let's go. So let's say I'm putting X's in blue that represent where crest and crest meet, and that represents constructive interference, right? Here, if I have two spaces as well overlapping, I would have constructive interference as well, because that shows me trough and trough. Now, if I wanted to put, let's use orange color, right? Right. So my orange color now would be, let's say, the green overlapping with the space in the pink. Then that is crest of one, trough of the other. That's destructive. So all of these lines show destructive. In the same way, where this line meets the space in the green, that shows destructive, because that shows you have both crest in one and trough in the other overlapping.